All right, welcome everyone. Pleasure to see so many here in the live audience. Our speaker today is none other than Michael Bronstein, who will talk about physics-inspired GNNs. And without much further ado, Michael, the floor is yours, and I'm really excited about your talk.
Thank you very much. Thank you, Bastian, for the introduction and for the invitation to speak here. So I would like to talk today about more or less recent works from the past couple of years that together with colleagues we've been working on in exactly this direction of how to design graph neural networks and related approaches that draw inspiration from physics. So I should say that in general, in the field of geometric deep learning, physics is a kind of an analogy or an inspiration that accompanies it from the very beginning. And maybe starting a little bit far, I like to open with this quote of Weil, who was himself a mathematical physicist that contributed a lot to the creation of modern physics as we know it in the 20th century. And he identified symmetry as probably one of the most important concepts in science, and described it a little bit poetically as one idea by which man through the ages has tried to comprehend and create order, beauty, and perfection. And symmetry originally is a geometric concept, even though, of course, it can be understood in a much broader sense. And as you know, geometry takes its roots from antiquity, but probably first time vigorously formulated by ancient Greeks. And for more than 2000 years, the Greek version of geometry, the Euclidean geometry, was the only one that is still probably nowadays studied at school as the geometry. And after many unsuccessful attempts, it was finally in the 19th century where the monopoly of the Euclidean geometry was broken and different other types of geometries were found that were inconsistent with in particular, the fifth postulate about parallel lines of Euclidean geometry. And this kind of zoo of different geometries required an organization and a revisiting, which came from Felix Klein in 1872. So he proposed a radically new concept of approaching geometry as the study of space with some transformation groups. So you look at geometric objects, you subject them to some class of transformations, and you see what remains intact or invariant. And these kind of symmetries, right, formalized through the language of group theory, gave rise to different geometries, and you could immediately say which geometry is more general than the other. And he was very fond of projective geometry in particular. He was also able to link it to constant curvature geometries, in particular hyperbolic geometry that was proposed before by Lobachevsky, Boyer, and presumably also Gauss. It took another approximately 50 years to integrate the more general Riemannian geometry that was developed around the same time. And the evolution of this concept in a more abstract setting also was the birth of category theory in the 40s. In the past century. So it was very, I would say, not only direct, but also cultural impact in mathematics outside geometry. It also had very big impact in physics. So the Erlangen program, as Klein's approach was called, in the 20th century brought the realization that you can derive conservation laws in physics that so far were empirical from pure conservations from first principles of symmetry. This is an example of the famous Noether theorem. And then these ideas were generalized by Weil through the notion of gauge symmetry, and Young and Mills, who were successful to unify different types of forces. And but this is the physics that we know nowadays. So they typically distinguish between what is called external symmetries, so what is called the Poincaré group that gives rise to the Minkowski geometry of special relativity, and the different symmetries of fields that are responsible for different types of interactions. And I think it's hard to formulate it more laconically than done by Anderson, that it's only slightly overstating to say that physics is the study of symmetry. Now, what does it all have to do with deep learning? And in deep learning, we also have this kind of zoo of different architectures that historically were developed for different types of settings or different types of data, like convolutional neural networks that were developed for image data, for example, or recurrent neural networks for sequence data, or graphs that originated in chemistry, actually, graph neural networks that were basically molecules that are modeled as molecular graphs. So geometric deep learning is a kind of geometric unifying framework in the spirit of Klein's Erlangen program that tries to bring a common denominator under all these architectures. And the idea is that you treat the inputs to neural networks not as just high-dimensional vectors or points in high-dimensional space, but signals that live on some geometric domain, typically low-dimensional one, right? And we have a domain with some associated symmetry group. We have signals that live on this domain on which the group acts for some representation, and then we have functions that take as inputs these signals and they respect the underlying symmetry. And convolutional neural networks are probably the most straightforward and classical example. So there the domain is a plane or a grid. The group is the translation group, and we have images that are defined on the grid and Shift operators that are representation of the translations. And then convolutions are equivariant functions that commute with the Shift operator. So I will be talking today about graph neural networks. So graph neural networks are also a special case of this geometric deep learning blueprint. Here we have the permutation group as our basic object, basically reflecting the fact that we don't have a canonical ordering of the nodes of the graph. Then we have data that lives typically in the nodes of the graph, and then message passing are the types of functions that are used in graph neural networks that are equivariant with respect to these symmetries. And I think I don't need to convince you that graphs are interesting objects. So they are more or less ubiquitous in every field of science, from chemistry, where they are used to abstract and represent some of the smallest entities like molecules, to the very large scale of, for example, social networks, studying how people interact with each other. So for the discussion of graph neural networks, allow me to assume some simplistic setting, and this can be, of course, made more complicated, but just to make things simple. I will assume that the graph is undirected, that we have decorated nodes with d-dimensional features, and basically the structure of this graph and the structure of its features can be represented by the adjacency matrix and the feature matrix. And one thing that is important to note here is that while the graph itself, being a topological object, doesn't have any particular ordering, when we represent its structure as a matrix, we must assume some ordering that is arbitrary. So the way that I represent the graph and the attached features on the computer will depend on how I order the nodes. And because I don't have a canonical ordering, anything that I do with these representations must account for the fact that there is this inherent ambiguity. Now, when I want to solve learning tasks on graphs, typically we can distinguish between two types of tasks. So in the first case, I want to predict graph level property, like if I have a molecule that is modeled as a graph, I want to predict its chemical or physical properties like solubility. Or in another example, I might have, for example, a social network with different users, and I would like to find some badly behaving users like spammers. So in the first case, I am interested in functions that no matter how I change the order of the nodes in the input graph, I get the same output. So we're talking about permutation invariant functions. In the second example of finding spammers on a social network, the output has the same structure as the input. So we are outputting some predictions for the nodes of the graph. So if I change the order of the nodes, the output should change in the same way, right? So these are permutation equivariant functions. And graph neural networks essentially consist of layers of permutation equivariant functions that might be followed by some kind of aggregation or pooling layer that contracts everything into a single vector, a single number, and that's the graph level prediction. So the way that these permutation equivariant layers are implemented are in the form of neighborhood aggregation, or what is often called message passing. So if I look at a node in the graph, let's call it node I can look at the nodes that are connected by an edge, right? So the neighborhood of node I, and look at the features attached to these nodes. And if I aggregate these features, basically I have a set, or more technically correct, a multi-set that I remind you doesn't have a canonical order, right? So basically I can have any ordering of these neighbor features in this set. So the way that these features are aggregated must be done by a permutation invariant function, right? That I denote here by phi. Now, if I apply this function at every node of the graph, I get an output, right? Node-wise output of the graph neural network that will be permutation equivariant. And the choice of this function phi, right, this local aggregator, is actually very important. And most of the graph neural network architectures differ in the way that this function is defined. And most of the architectures, or at least the more traditional architectures of the message passing type, fall into three different categories or different flavors, as we call them. So the first flavor is what is called convolutional graph neural networks. So in this case, we aggregate the neighbors, let's say by a summation, but it can be any permutation invariant aggregator. we subject the neighbor features to some learnable transformation that I denote here by psi. And then the aggregation is with some coefficients that do not depend on the features. They depend only on the structure of the graph. For example, can be, in the simplest case, be just the elements of the graph adjacency matrix. And sigma here denotes some nonlinear activation. So this is how a single layer of a convolutional GNN looks like. And in most cases, the transformation is actually a linear transformation. So we have this matrix W that is shared at every node, and then the aggregation can be written as a big matrix of size n by n that is called diffusion or a diffusion matrix. And this is the simplest instance of a graph neural network that you can think of. It is highly scalable, and it has found many applications in industrial settings. So I think the first one was Pinterest to use GraphSage, which is a convolutional version of GNN. We also developed some similar methods at Twitter. So the folklore has it that these kind of methods work only for homophilic graphs. And by homophily, I mean that the neighbors of the nodes are similar to the nodes. And basically, you can say something about the node from looking at its neighbors. And usually the intuition that is given is that the matrix A looks like a low-pass filter, right? So it averages the neighborhood of a node, and if the neighborhood is heterogeneous or heterophilic, or you have different information, then basically you're mixing together some completely irrelevant information, and basically it doesn't work well. So this statement is not true. So this, I will show you that this folklore actually is not correct, and the reality is much more subtle, and there is also the channel mixing that interacts together with the diffusion matrix, and it's their interaction that determines whether this aggregation works properly or not. So the second flavor that I would like to mention are attentional graph neural networks. So again, this kind of summation-based aggregation. Now the coefficients are not only dependent on the structure of the graph, but they're dependent on the features, typically through the attention mechanism. And the most general flavor are generic message passing architectures, where we have a bivariate function that depends on the pair of features of the node itself and of its neighbor. And important result from a few years ago, it actually probably has been known for many years before, but let's say in the context of GNNs, it was first shown in 2019 that the expressive power of message passing GNNs is upper bounded by the Weisfeiler-Lehman graph isomorphism test. And this happens when we have injective aggregation. And it is a classical result in graph theory from the 60s, actually inspired by problems in chemistry, trying to determine structure similarity of organic molecular structures. And basically, it's an iterative color refinement procedure that was devised by Andrea Lehman and Boris Weisfeiler. They initially believed to have found a polynomial time algorithm for determining whether two graphs are structurally equivalent or isomorphic. So it goes like this. Basically, we start with a graph where every node is labeled in the same way. So it essentially ignores the features that are attached to the graph. It considers only its structure. And it examines the structure of the neighborhood of every node. So here, initially, we have two types of neighborhoods. We have blue node with 3 neighbors and the blue node with 2 blue neighbors, right? That looks like this. And if we assume that this function phi is injective, we can think of it as some form of hashing, then it will produce 2 different labels, right? So I can refine the color of the graph. And now we have this graph that we have 2 colors. Let's call it green and yellow. So I can repeat the procedure again. Now we have 3 types of neighborhoods. We have green with 1 green and 1 yellow neighbor. We have green with 2 yellow neighbors, and we have 1 yellow with 2 green and 1 yellow neighbors. And these will become respectively gray, violet, and orange colors. So if I repeat the procedure again, now the colors will not change, at which point I can stop and produce a distribution of colors, a histogram. And by design of the algorithm, we can show that if I give you another graph that produces a different histogram, I can for sure guarantee that the graphs are not isomorphic. But if I get the same histogram, like in this example, actually, I don't know. So it's a necessary but insufficient condition. And in fact, you can find even very simple examples of graphs that would be deemed equivalent or indistinguishable by the Weisfeiler-Lehman algorithm, but they're not isomorphic. And one example is, for example, graphs containing triangles. So it's actually, to me, it's very surprising that this method came from organic chemistry, but actually there are plenty of examples from chemistry, different molecules of non-isomorphic graphs that cannot be distinguished by the Weisfeiler-Lehman test. So this realization of bounded expressive power has actually led to a Cambrian explosion of different, more expressive graph neural networks in the past couple of years. And I don't have time to go through all of them, but roughly speaking, you can put them probably most of them into 4 following categories. So it's either higher order Weisfeiler-Lehman tests or some form of positional or structural encoding. It's also different versions of subgraph GNNs, where you consider instead of a graph, a collection of subgraphs that is extracted using some policy, or high dimensional topological message passing, where you take a graph and you construct some high dimensional object, such as cellular or simplicial complex. So regarding the higher order WL tests, basically it's an entire hierarchy of tests that originally was developed by Laszlo Babai and collaborators. And basically, for each of these high dimensional tests, you can always find families of graphs that would be indistinguishable. Like the standard regular graphs would be indistinguishable by the standard WL test. There are strongly regular graphs, or what is called CFI graphs, that would be indistinguishable by KWL. And as I mentioned, the standard message passing is equivalent to the standard WL test, and Maron and collaborators have constructed the higher order equivalents of the KWL test that unfortunately are not really computationally tractable. So they're mostly good for proving theorems. So the class of more expressive graph neural networks that are based on positional or structural encoding. So one simple example is what we call graph substructure networks. So you can simply say that let's count substructures that the WL test cannot detect, like triangles or maybe cliques or maybe cycles. And this way we can get a class of algorithms depending on the choice of these substructures that are actually outside of the KWL hierarchy. So we can make algorithms that are not less expressive than can the KWL. And it especially works nicely when we know a priori in the problem what kind of structures might be prominent. So this is an example of molecular property predictions, where you can see that by infusing the graph neural network with the counts of cycles, for example, we can get significantly lower error in predicting some molecular properties like water solubility. And that's not surprising, because properties like structures like cycles, what is called aromatic rings in chemistry, are very prominent in organic molecule, right? And this is a molecule of caffeine, which has a 6 and a 5 cycle. Now, if you look at it from a broader perspective, basically the traditional approach to graph neural networks starts with the input graph, right? And you use the same input graph as a computational device to propagate information on the graph. And we can enrich it in different ways, right? For example, with positional encoding, or we can lift the graph into a high dimensional space and do message passing on, for example, simplicial or cellular complexes. As I already mentioned, we can consider a collection of graphs with the product symmetry group. We can also account for the symmetry of the data, right? And this is especially important in geometric graphs like molecules, where the features actually live in continuous space. So we want to account, for example, for their rotations and translations. So there are other classes of techniques that can be considered conceptually as graph neural networks, where, for example, we can decide to completely ignore the graph. And in this case, we are working on sets. So deep sets or point nets are essentially graph neural networks with no edges. On the other hand, we can say that I allow for any pair of nodes in the graph to interact. So we have a complete or fully connected graph. And basically, I can infer the graph that is good for the downstream task, using, for example, the attention mechanism. So that's what transformers do. And of course, transformers that are used in NLP applications, sometimes you want them to express non-permutation invariant functions, so they heavily rely on positional encoding. So it is interesting that actually a lot of approaches do something in between these two extreme cases. Sometimes you say that I don't maybe completely like my graph that is given as input, so let me retouch it a little bit. And these class of approaches are called graph rewiring, and then I will do propagation on this new graph. And one of the reasons for this is that some graphs might be unfriendly for message passing. So what you can see here, there is a graph with a bottleneck, and depending on the task, for example, if my task requires me to send messages from one click to another click, it all has to go through this narrow bridge. And as a result, I might run into problems that are called bottlenecks and oversquashing. So I might want to facilitate the flow of information, the message passing, by maybe removing or adding some of the edges in this graph. So there is plenty of graph rewiring techniques, and there is a little bit, I think, strong opinions in the field about how come we cannot touch the sacrosanct graph, right, that is given as the input, right? But de facto, a lot of graph neural networks do some form of rewiring, starting from neighborhood sampling, right? If you have a very large graph where the degree of the nodes can be very high, I cannot just technically, computationally look at all of them, so I will be sampling them, right? So here you go, it's some form of graph rewiring, right? Or if, for example, you also want to bring information from multi-hop neighbors, right? For example, neighbors of the neighbors, so you also de facto rewire the graph. So what happens, bottom line of this is that we have a gap between theory and practice, right? So we have the Weisfeiler-Lehman formalism that assumes explicitly that I use the input graph to propagate information. And by doing so, I can discover somehow, maybe partially, the structure of the graph. But it doesn't account for the situation when I can change the graph on which I propagate. So this is something that we would like to challenge. So we would like to talk about expressive power without necessarily restricting ourselves to the rigid input graph that is given to the graph neural network. Another thing that is interesting to look at is if we look at these different objects that we encounter in the universe of geometric deep learning methods. So we have graphs on the one side, we have meshes, right? You can think of them as graphs with some extra structure. So these are simplicial complexes. And we have grids, which are again graphs with maybe some regular structure. So if I look at the way that I aggregate information on the grid, I don't have any ambiguity, right? Because I have canonical order of my neighbors. So I can designate a neighbor at the top, a neighbor on the right, and so on. In the case of meshes, the situation is slightly different. So I can select the first neighbor in a neighborhood, right, in one ring or one hop neighborhood, and then order all the neighbors, for example, in clockwise orientation, because meshes are discrete manifolds, so they have local Euclidean structure. But the choice of the first neighbor is arbitrary, so I can define it arbitrarily up to rotation, right? So we have some ambiguity, but it is kind of mild ambiguity. And in case of graphs, any permutation would, as we've seen, would work, right? So in some sense, graphs have the least structure among these objects. Another thing that you notice that, again, if you look at grids and meshes, we can consider them as discretization of some continuous objects. So a grid would be a discretization of a plane, for example, and the mesh would be a discretization of a surface or a manifold, right? We don't have such an immediate analogy for graphs, right? Of course, there is an entire field of network geometry, right, which tries to come up with continuous models, but in general, it's something that is a little bit less obvious than in the first two cases. So this is exactly what we try to do with, well, a different perspective, I would say, on graph neural networks that comes from inspiration in physics. And for the remaining part of this talk, I invite you to consider graph neural networks as dynamical systems. So think of nodes of the graph as some kind of particles that live in maybe some high-dimensional feature space, and they move along certain trajectories that are driven by this system of differential equations. So here again, X is a matrix of features, T is continuous time, and there is the system of differential equations that are coupled through some function F that is parametrized by some trajectory of parameters theta. Okay, so here the layers are just discretization of time. So I can just take some samples, maybe with fixed step size or maybe a different step size, doesn't really matter, and say that this is a layer. So a layer here doesn't really play any crucial role, right? Same way as the depth, the number of layers, because it depends on how I discretize my time. I can have many layers or few layers. So it's more the evolution time rather than the actual number of samples that plays an important role. So the graph here plays the role of a coupling function that I denote here by F. And as I will show, also in some instances, you can think of it as a discretization of some continuous object, some continuous space. So out of all possible evolution equations of these differential equations that describe how these particles or the nodes of the graph evolve, probably the first thing that comes to mind is a diffusion equation, right? And this is one of the phenomena that has been studied mathematically, probably among the earliest ones when physics was still a kind of semi-alchemy, and by none less than Sir Isaac Newton himself. And he looked at how objects exchange temperature experimentally, and then came up with a mathematical model that nowadays we call the Newton law of cooling. And it tells us that a temperature that a body loses in a given time is proportional to the temperature difference between the object and the environment. So it's a kind of a global rule But if we make it local and we apply it to graphs, this is how it looks like, right? So we have, let's say that the color here represents the temperature of the nodes on the graph, and instead of temperature, you can think of any other stuff or any quantity that diffuses on the graph. So the left-hand side here represents the rate of temperature change, right? So that's the temporal derivative. The feature of the node itself, it's the self-temperature, and then here we have in red the temperature of the environment, right? So that's the average of the neighborhood. If I slightly rearrange these terms in this formula, what I have on the right-hand side is the gradient of the graph gradient of this node field, and what the sum is the divergence, right? So I look at the differences between the features at endpoints of an edge, and then the gradient is edge-wise signal. So I collect the gradients over all the edges that emanate from node I. So this is the divergence, and together I can write it as the divergence of the gradient or minus divergence of the gradient, as we prefer. And this is called the Laplacian operator. So it's a positive semi-definite operator, a positive semi-definite matrix. And this is how the simplest homogeneous diffusion equation looks like on a graph. So you can write it in this very simple linear differential equation. Now, the heat equation is also a prototypical example of a gradient flow. So gradient flows are a special type of evolution equations where the evolution is driven, it goes in the negative direction of the gradient of some energy. And the energy that corresponds to the heat equation is what is called the Dirichlet energy. So it measures how smooth the node features are. And we can show that it decreases along the flow. And in the limit, when t goes to infinity, basically everything will become constant, right? So the Dirichlet energy will go to zero. And it means that basically my neighbors are not distinct from me, right? So everything is constant. So this is a phenomenon that is typically considered undesirable in graph neural networks. We call it oversmoothing, but in fact, it might be actually a good idea, because if we assume that our data is homophilic in the sense that my neighbors are similar to me, actually this idea can be used straightforwardly by just doing label propagation. So I can say that if I want to predict the label of my node, I will look at my neighbors and propagate this information. And if under the assumption of homophily, it will be a good guess of what the label of the node is, right? Of course, if the graph is heterophilic, then it doesn't work. Now, the standard mindset of graph neural networks is to take this evolution equation and parameterize it, right? So I will discretize it in multiple steps that correspond to layers of a graph neural network, and I will typically parameterize each of these layers, right? So what I'm trying to convince you today is that instead of this, you can pick up an energy functional and parameterize this energy, and then the evolution equation will be derived as a gradient flow. So I'm already restricting the class of evolution equations. It's not anything that appears on the left. It's a special type that can be written as a gradient flow. What we'll get in exchange, basically, it will allow us to make smart architectural choices that have provable properties. So I call it interpretability, which is maybe a little bit lauded term in machine learning, but what I mean by this is that I will be able to make statements about the behavior of such a graph neural network. Now, the kind of energy that we consider is what we call generalized parametric Dirichlet energy. So it has, it's parameterized by two d by d matrices, omega and w. And it has two terms. So the first term is, you can think of it as some kind of external energy that acts on all the particles. Think of everything moving by some external force. The more interesting term is the second one, which is an internal energy. It defines the interactions between nodes along edges of the graph, right? So think of particles that interact with each other along the edges of the graph, and the interactions can be of two types. They can attract, and this happens along the positive eigenvectors of the matrix W, or they can repel, and this happens along the negative eigenvectors of W. And here you can see an example of how it might look like. So the circles here, their positions represent two-dimensional feature coordinates. So here the nodes evolve in a two-dimensional space, and the colors represent different labels or different types of nodes. So you can see here a perfectly heterophilic graph, right? So every node is connected to nodes of different colors, and yet you can find directions, right? So horizontal direction is where repulsion happens, and vertical direction where attraction happens, that can perfectly evolve these points completely separated, right? So that would achieve perfect classification of red and blue nodes. So even though this graph is heterophilic, this kind of evolution is able to perfectly classify the nodes. So this has to do, as we'll see, with this folklore statement that convolutional type of graph neural networks are not suitable for heterophilic graphs. So already here you can see a kind of taster of what will be next. So this is an example of where it actually does work. So we want to understand why actually this happens. And if you look at the gradient flow of this energy, one thing that you notice is that the matrices that parameterize it appear in symmetrized form, so we can assume without loss of generality that we're talking about symmetric matrices. So basically, the symmetry constraint comes from the assumption of a gradient flow. Also, we see here by the way that we design the energy that these matrices are time independent. So basically they will be shared across different layers. And if we discretize this gradient flow, we get a residual type GNN of convolutional type. And when I say convolutional, again, I mean that the diffusion operator that appears here, the matrix A, is constant. It depends only on the structure of the graph. It doesn't depend on X. So the residual type of architecture comes from the discretization of the temporal derivative. The weights are symmetric. So again, this comes from the gradient flow. And we know from previous results that actually it doesn't diminish the expressive power in the sense that we still have universal approximation properties. And the weights are shared across layers. So the way that this is applied to node classification problems is you start with some features that live in the nodes of the graph. You can optionally apply some encoding to them. Then you run the gradient flow, which is linear, which is important. And then you do some decoding that reads out the outputs. And it can be either node-wise or it can be graph-wise. So if we compare this architecture to the standard GCN architecture that was proposed by Kipf and Welling. So there are several things that you notice that are different. First, it's residual architecture versus non-residual in the case of GCN. We have symmetric weights versus general matrices in case of GCN. The weights are shared in our architecture, and in GCN they are different across layers. And we don't have any nonlinear activations, right? So that's the sigma that appears in GCN. And this is a kind of goes against the usual mantra of deep learning where that says that you need to have nonlinear activated layers. Each of them should be parameterized differently. So nothing like this in the gradient flow framework. What we get in exchange is that we get some interpretability. It's a gradient flow. We have less weights, right? So it's independent on the number of layers. So the number of layers really doesn't matter. It's just how much you want the diffusion to run. And what is the most important is that the gradient flow, as I will show in a second, can induce both low and high frequency dominated dynamics. And as a result, we can work with heterophilic graphs, so we can avoid oversmoothing. Okay, and the way that to visualize it, how it looks like. So here is a data set that is called synthetic Cora. So it's a citation network where nodes represent papers and edges represent citations. And the graph is designed in such a way that you can change the level of homophily. So in the most homophilic case, it will look like this on the left, where the neighbors are similar to the nodes themselves. And in the worst case, right, when it's mostly heterophilic, then the neighbors will be different with different labels. So here we can have two extreme cases. So we can ignore the structure of the graph whatsoever and do just node-wise classifications, right? Apply node-wise multi-layer perceptron, and it gets to certain accuracy, about 65%, which is completely independent of the level of homophily of the graph, right? Because we ignore the graph, we don't use it. The other extreme case is we can use a GCN, and GCN works perfectly when the graph is homophilic because our neighbors contain similar information to the node itself. So it basically averages them out, does a kind of denoising. So it reaches almost 100% accuracy when the graph is homophilic. But it degrades very fast when the level of homophily drops. So when the graph is completely heterophilic, it's more or less useless. It's about 30% of node classification accuracy. So you can see that the gradient framework allows to blend between these two cases. So it is as good as GCN in the homophilic case, and it degrades gracefully when the level of homophily of the graph drops. So another thing about scalability, if you write the output of this gradient flow framework, because it's linear, basically it boils down to just being a polynomial in the diffusion matrix A and the shared weights matrix W. So there are some dependencies between the weights W, but basically what you can do if you get rid of the encoder, and we show actually that you don't necessarily need a nonlinear encoder, you can pre-compute these pre-diffused features. So I can first compute the propagation of the features on the graph, and that's the most expensive part when you try to implement a graph neural network at large scale. I'm talking about graphs with hundreds of millions or even billions of nodes. And then the learning will boil down to just doing node level, very simple architectures like multi-layer perceptrons, maybe with dependent parameters. So, and we show that you can scale these kind of architectures to very large graphs. So that follows our previous work that we call SIGN. Now, the most important thing that I wanted to say is about this low or high frequency dynamics. And basically, given that our matrices are symmetric, right, both the Laplacian and the channel mixing matrix, the channel mixing by virtue of the assumption of gradient flow, right, we assume that the matrix is symmetric. The matrix delta, the graph Laplacian, by virtue of assuming an undirected graph. Basically, we can compute Fourier basis for both of these matrices and now write the output of the graph neural network in the Fourier basis, right? And here you can see that we have this interaction between the different sets of eigenvalues, the eigenvalues of the graph Laplacian and the eigenvalues of the channel mixing matrix. And we see that the low frequencies of the graph are magnified by positive eigenvalues of W, and the high frequencies are magnified by negative eigenvalues of W. So here we get, it's not just a low pass filter, as the folklore would say, there is this interaction between the spectra of both matrices. And what we show in the paper is that if the eigenvalues of W are sufficiently negative, then we can probably show that we induce high frequency dominant dynamics, in the sense that the Dirichlet energy of the features will not converge to zero. So in other words, we avoid oversmoothing. So that's what allows us to deal with heterophilic graphs. So we can incorporate correctly the information from different nodes in the neighborhood. Now, of course, this was a very simple diffusion equation that was homogeneous. So we can consider more complicated equations, and here we draw inspiration from image processing, from variational and PD-based methods that were developed in the 90s in this field, starting from the seminal paper of Perona and Malik on non-homogeneous diffusion that they actually incorrectly called an isotropic diffusion. And the idea is that when you run a filter on an image, you can think of it as the simple linear filter, you can think of it as a diffusion equation, right? So that's a low-pass filter. And of course, it produces something undesirable, like what is shown here in the center. So that's just simple low-pass filter conversion with a Gaussian, right? That's what heat diffusion will produce. So it removes noise, but it also destroys the discontinuities in the image that are important for visual perception. So the idea of non-homogeneous diffusion is to control locally the speed of diffusion with some edge indicator function. So it will slow down or completely stop when you reach a discontinuity. And that's how the kernel of this diffusion equation will look like. So it produces results that you see here on the right. So it both does denoising in piecewise continuous or piecewise smooth regions, and it doesn't mix pixels of different colors. So we can write a similar diffusion equation on graphs. So here again, we have the graph gradient, we have learnable diffusivity function and the divergence. And if we discretize it with explicit forward Euler scheme with fixed timestamp, we get a generalization of the graph attention network. So GAT can be considered as a particular discretization of the graph diffusion equation. Now, so far, initially I promised you to propose a continuous version of graph neural network. So far, what we have continuous is only the time, right? And if we take a step back and think of how diffusion equations look like in Euclidean space, right, on a plane, for example, when I discretize it on a grid, I don't have really a canonical discretization of my differential operators. So if these are three different ways I can discretize the Laplacian, for example, in 2D, right? Or because it's a linear operator, any convex combination of these operators will also be legitimate discretization of the Laplacian. So what I'm trying to say here in short is that we don't really have a kind of canonical graph when we discretize differential equations in continuous case. And I would like to adopt a similar stance for graph neural networks. In order to do it, again, I would like to draw an analogy from image processing. So if so far we considered some nonlinear diffusion equation like Perona and Malik, we can also consider a non-Euclidean version of the diffusion equation. And here, if we think of images, we can think of them as two-dimensional manifolds that are embedded in a joint space where you have a combination of feature coordinates and positional coordinates. So a color image, for example, would be a two-dimensional surface in R5, right? We have X, Y, R, G, and B coordinates. We can pull back the metric from this space, and we can define a diffusion equation with on this manifold that uses a non-Euclidean version of the Laplacian operator, what is called the Laplace-Beltrami operator. And it is also a gradient flow that minimizes a generalization of the diffusion energy that is called the Polyakov function. It's used in string theory by physicists. So the analogy of this equation on the graph would be to think of a graph that has two sets of coordinates attached to every node. We have positional coordinates that I denote by U and feature coordinates that I denote by X. And we have the evolution of both components by a learnable diffusion equation. So the learnable part here is the coupling function A, right, or the diffusivity function A. And the evolution of the X component is the standard feature diffusion. The evolution of the U component, you can think of it as some form of graph rewiring. So if in the positional space, two nodes become closer, I can decide to introduce an edge between them to facilitate the flow of information. And likewise, if they drift apart, I can decide to disconnect an edge between them. And I know that this explanation sounds cumbersome, so here is much better illustration of this, of what is happening here. So this is again the Cora graph, and the circles here represent nodes. The color of the circles represent a three-dimensional projection of the features, and their positions represent two-dimensional positional embedding. And you can see here that three things happen at once. So we have the feature diffusion, right? So the colors of the nodes are changing. We have the positional encoding also changing, right? So the clusters drift apart. And also the graph is changing on the fly. So we are rewiring at every iteration. And we see that here we are able to get very nice separation, very nice clustering into 7 categories, which is exactly what the original task on the Cora graph is. And if you think of it from the signal processing perspective, basically we have this kind of a little bit schizophrenic picture here. So we are doing filtering on a domain that is changing at the same time as we are doing filtering, right? So a kind of moving ground, which is a little bit disturbing if you come from the perspective of signal processing, but totally acceptable if you come from the field of differential geometry. And differential geometry is like taking a domain, a manifold, and subjecting it to some evolution equation. And typically, it has this form where we have evolution of the Riemannian metric, right? And probably the most famous instance of these evolution equations are Ricci flows. So they look structurally very similar to diffusion equations. On the left-hand side, we have the temporal derivative of the Riemannian metric. On the right-hand side, we have a second order quantity that is called the the Ricci curvature tensor, which is a little bit similar to the Laplacian. And if I take a manifold that looks like a dumbbell, right, which has positive curvature and negative curvature in the bridge, if I run a Ricci flow on it, then it will become more like an ellipsoid than like a sphere and then collapse into a point. And this formalism was introduced in the 80s by Richard Hamilton with the goal of proving the Poincare conjecture. So the way that you can characterize a topological sphere is by whether you can take a closed curve and collapse it into a point. You cannot do it on a torus, right, where you have a curve across the donut. So basically, Poincare conjecture, that's also a way of characterizing three-dimensional spheres. And as you probably know, it was used by this formalism was used by Perelman about 15 years ago to prove the Poincare conjecture that was an open question in topology for more than 100 years. Now, what does it all have to do with graph neural networks? In graph neural networks, I already mentioned this phenomenon of bottlenecks and overscorching, which happens when we have a graph where the volume grows exponentially fast. And this happens, for example, in trees or small world networks, where the number of the neighbors of the neighbors of the neighbors increases exponentially. And our problem requires to bring information from distant neighbors. So we have long-range dependencies. And mathematically, you can formalize it as some form of lack of sensitivity. So if I consider a message passing neural network of this form, and where L is the number of layers, P will be the width, and the nonlinearities will be Lipschitz continuous with some bounded weights, then I can ask how the output at node I depends on the input at node J, right? That is distant from I. And I can quantify, basically do this sensitivity analysis. I can write it as a Jacobian, right, as this partial derivative of the output with respect to the input. And we can show that you can bound this Jacobian by some constants that depend on the model of the neural network, as well as on the topology of the graph, right? And oversquashing means that this Jacobian is small. So I have low sensitivity of the output with respect to the input. Now, if you look at how different components of this bound participate, for example, what we show is that width helps mitigate oversquashing, of course, with the usual downsides like worse generalization and overfitting. The depth actually doesn't help. And I remember a couple of years ago, I wrote this controversial blog post about depth being considered harmful in Graphql Networks, and I received a lot of criticism for it. So at least from this standpoint, it still holds in my opinion, so depth doesn't help. And the most important role, of course, is played by the topology. And this is intuitive because we know that, for example, graphs like grids are more benign, and usually we don't see oversquashing there, but other structures like trees are actually much worse. And there we would expect the worst sensitivity. So if we look at this bound, right, so we see here that the structure of the graph enters through the power of the adjacency matrix, but it's not clear how, right? So we need something more nuanced and more subtle to analyze different types of graphs. And that's exactly where an analogy from differential geometry that I mentioned before, the Ricci curvature, can be used. And the way that you can think of curvature in differential geometry is as what is called geodesic dispersion. So if I take nearby points and shoot geodesics from them in parallel, I can see whether they converge, remain parallel, or diverge. And this allows me to distinguish between spherical, flat, or hyperbolic spaces. So by analogy, on a graph, I can say that I have adjacent nodes, P and Q. And if I look at edges emanating from them, I can see whether they form triangles. So I'm looking at clique-like structures. If they form rectangles, I'm looking at something that looks locally like a grid. Or if they drift apart, I'm looking at tree-like structures. And without going into too much details, we can define edge-wise quantity that we call balance form and curvature. So it's a discrete graph analogy of the Ricci curvature that is a combinatorial quantity. It counts certain types of rectangles and triangles. Doesn't really matter what exactly it is. What is important that it reproduces the continuous behavior. So cliques are positively curved, grids are zero curved, and trees are negatively curved. And the main result of the paper is we show that if we have strongly negatively curved, basically the curvature is lower bounded by some negative delta, we can bound this Jacobian. So basically, we can attribute oversquashing to strongly negatively curved edges. And once we know this, we can actually propose a procedure that is inspired by the Ricci flow that surgically removes these negatively curved edges from the graph and replaces them with edges with positive curvature. So we can, by touching a little bit the graph in a surgical way, we can improve it significantly and make it friendlier for message passing. And we show that it works also in heterophilic settings where previous graph rewiring techniques such as Diggle, which is based on diffusion, do not work well. Now, in the interest of time, let me just finish with one last example, and this is an example of more exotic stuff. This was work that was done in collaboration with Chris Bodnar, who is now at Microsoft. So he was a long-term intern at Twitter when Twitter had a research division before the end of last year. And basically, the idea is that if you consider graphs by analogy to manifolds, so manifolds are purely topological objects, right? So you can think of them roughly as spaces where you have the notion of who is your neighbor, but not notion of distance or angle, right? So in order to have this notion of distance or angle, you need to equip the manifold with extra structure that typically comes in the form of an affine connection that allows you to transport vectors from one point to another. So this is parallel transport, or in the form of metric. And again, there is a special connection that is called the Levi-Civita connection that is compatible with the Riemannian metric. So same way with the graph. So graph is purely topological object, but if you want to define how you transfer information from between nodes and edges, you can lift it into a more complex structure that is called the cellular shift. And basically, it's a collection of vector spaces that are attached to every node and every edge, and linear maps between them that are called restriction maps. So basically, by doing this, by constructing a cellular shift on top of a graph, we equip the graph with some geometry, and basically in this object, we can study diffusion equations and see actually what they can do with node features. And these diffusion equations, we show that they have more interesting and richer behavior than the standard diffusion equations on the graph. And again, here, the diffusion equation will look exactly like before. So the delta F is the shift Laplacian. So defined exactly as before, divergence of the gradient, where the only difference now is that when I compute the gradient, I cannot just subtract two endpoints of an edge. I need to apply the transformation that basically brings parallel transports, if you wish, the feature from my neighbor to myself. And I can let this diffusion run with some initial conditions to infinity. So I'm studying the asymptotic behavior of the diffusion equation, and we can ask, for example, how many node classes we can distinguish by this process. And you can see here some examples that actually we might have multiple node classes that can be separated. So it forms a kind of alternative to the Weisfeiler-Lehman formalism that doesn't stick to the graph isomorphism hierarchy. So it's not rigid in the sense that we don't necessarily need to assume a fixed input graph. So because it's a differential equation, in principle, we can rewire the graph in different ways. And it also addresses the expressive power of node-wise classification, whereas Weisfeiler-Lehman considers graph classification and graph isomorphism testing. So this physical or PDE-based perspective, I think it offers a fresh look on old problems like oversmoothing and bottlenecks. It allows to interpret old architectures from a different viewpoint, but it also potentially allows to design new architectures, whether by using, for example, more sophisticated solvers or by making principled architectural choices, like whether we use residual connections or whether we use symmetric weights or we share weights across layers, right? So we can provide in some cases theoretical guarantees, such as, for example, lack of oversmoothing, like we had with the gradient flow framework. And I think more generally, it establishes deep links to other fields that are probably less known in GNN literature, such as differential geometry and algebraic topology. And I talked mainly about diffusion equations, but of course we can talk about other physical models like this work that we did with Konstantin Rusch and Sid Mishra from ETH Zurich, where we considered a coupled system of graph oscillators. So the best analogy here is these kind of oscillators that are coupled by some medium, right? So you probably have seen these kind of pictures many times. So in this case, the interactions are happen on a graph. So it's not everyone coupled to everyone, and the coupling is learnable. So we have some parametric coupling function, and basically this is a combination of diffusion type equations with oscillatory wave type equations. And we show, for example, that we can probably avoid oversmoothing. So I think I will stop here. Thank you very much for your attention. I will be more than happy to answer any questions that you might have.
Thank you very much, Michael, for great talk. Let's all unmute ourselves briefly and clap for Michael. I have to say, amazing illustrations. I don't want to hog too much time with dribbling over these great visuals. We have two questions in the chat. Maybe I'm going to start with the one by Vladimir, which came a little bit later, and then we move on to the one by Julius, because the one by Vladimir, unless I'm mistaken, pertains to the sheaves. And he asked, can you please clarify what goes into the definition of the sheaf?
Yeah, so well, a sheaf is an object in algebraic topology. So here we use what is called a cellular shift. So it can be defined on cellular complexes, but of which graphs are a particular instance. So basically, the sheaf is defined by taking a graph and associating vector spaces of certain dimension with nodes and edges. And then you have linear maps. Yep.
What is your fiber of your graph? So how do you design the restrictions?
So the restrictions, so it's a class of matrices that we can choose. So it can be general linear maps, or we can consider, for example, maps that are symmetric or non-symmetric. We actually show that different choices lead to different separation capabilities. So you can consider, for example, orthogonal maps. So in this case, it has a direct analogy to parallel transport on manifolds, to connection Laplacians that were studied by Zinger about 10 years ago. So we didn't do really an exhaustive study of this, but I think it's just an illustration that different choices lead to different outcomes.
And your shifts are always defined on graphs. So your cell complex is always just a graph, right?
Yeah. So we never tried to extend it to high dimensional cell complexes. We had also with Chris Bodnar another line of works where we considered message passing on cellular complexes. We never combined the two. So basically, he graduated and disappeared at Microsoft. But maybe at some point, he or somebody else would like to do it.
Thank you.
Very nice. We have another one. So now I'm going to go to use this question, because otherwise I think we're going to stay in this section for longer. So Julius has a general question, I would say, namely, do you believe that the methods available today can be extended to deal with graphs that are neither perfectly homophilic nor perfectly heterophilic, or do we need a fundamentally new approach? That's
a very interesting question. So I actually do have an answer, and this is a paper that we are submitting in the next few hours to NeurIPS, hopefully. So heterophily on its own is not necessarily a bad thing, right? So if you think of heterophily, it just means that your neighbors are different from you. And if, let's say, you have a graph with blue and red labels, right? And imagine a situation when you have a blue node that all of its neighbors are red, right? So this itself can be a rule that will allow me to classify my node as blue, right? So if all my neighbors are red, then I'm blue. So, and this is an example of perfect heterophily. So heterophily can be benign. Now, if we consider simple convolutional type graph neural networks that can be expressed as a polynomial in the adjacency matrix, then when your graph is directed, then you don't have just powers of the adjacency matrix. You have different possible mixtures, right? Like instead of A squared, you might have A transpose A or A transpose. And what we see is that actually these different matrices might have different level of homophilia. And so basically the way that you reach to your, in this case, two hop neighbors might be different. And in a sense, there was this primordial scene, if you want, of graph neural networks. So first of all, some of the methods, or at least the recent versions of graph neural networks, originated from spectral methods, from signal processing on graphs, where it was necessary to assume that the graph is undirected to construct Laplacian and do its eigendecomposition. Second, some of the first benchmarks like Cora were homophilic. So basically, people came to the conclusion that direction doesn't help. And if you use PyTorch geometric, for example, loading some graphs makes them automatically into undirected. So what we see is that when the graph is directed and heterophilic, actually using the direction correctly matters a lot. In some cases, it can improve. If you use the direction correctly, you can improve your performance by something like 10 to 20%. So that's the main message about homophily or heterophily, that on its own, it's not necessarily a bad thing. You just need to use in directed graph, you need to use direction correctly. So it's not fundamentally new approach. It's just taking a step back and reconsidering things that maybe were overlooked.
Right. Yeah. Thank you very much. So we have another question in the chat. I don't see a proper name there, so I'm not going to. I'm just going to read the question. So thanks for the amazing talk. I wanted to talk about where we're going with the generalization of message passing neural network paradigm, as there are evolutionary approaches over differential geometry structures. Another line of work involves making information diffusion more rich based on energies. So should we focus on making the information diffusion via processing the graph topology as in Ritchie-Flow rewiring work, or should we incorporate physics-inspired approaches? Or is it even possible to achieve this via moving from graphs topology towards higher dimensional manifold learning, so sheaves or Riemannian structures? Okay, that's a lot to unpack. Maybe let me know which types you want to answer, and then maybe you can take it offline for something longer.
Yeah, so let me talk about Ritchie flows and the rewiring and evolution. So I think what should happen is some kind of co-evolution of the features and the graph. So so if you think of rewiring approaches, right? So again, roughly we can talk about spectral approaches that try to perform to optimize some spectral property of the graph. That tend to add sparse connections, but that they break the locality of the graph, right? So they reach out to distant nodes. Or you have spatial approaches that, for example, try to bring information from k-hops, right? So they're local, but they're dense, right? So somehow you never satisfy all the properties. So you want the local inductive bias, you want to be sparse and therefore computationally efficient, and you want also, of course, you do rewiring to reduce the bottlenecks and oversquashing. So we have new results on different types of rewiring that allows to achieve these to achieve basically all these desiderata at the same time. So one of such papers is delayed message passing. It will appear. It actually appeared on arXiv already, so it will. It was accepted to ICML, and the idea there is that we propagate information from k-hops. We make it available to the node directly rather than being confounded together with information from the other neighbors. But we delay this information to a few layers next, right? Typically k layers next. So it's a kind of sparse skip connection, local skip connection in the graph. And we show that by doing this, first of all, we don't basically we can avoid over smoothing and over squashing. So we don't flood the node with features that are completely irrelevant. And another approach that actually does basically instead of doing a single rewiring does a sequence of rewiring operations and considers them together with the propagation of the features.
Very good. Thank you so much. So we are a little bit over time already. So I'm very happy to also move into offline mode now, or let you go back to those NeurIP submissions. Or are there any other questions? Does anyone have a public question, a short one maybe for Michael? If not, then thank you very much once again. I'm going to stop the recording, and then we maybe can have some additional questions. Thank you very much.
Thanks, Bastian. Thanks, everyone.